Today, let us talk on the topic nanomaterials, which is included in the module 3 of applied chemistry. We all know the term nano. The term nano is used for everything which is small. But in chemistry, a nanomaterial refers to a material with at least one of its dimension in nanoscale. It was Richard P. Feynman who introduced the concept of nanotechnology about 50 years back. A nanometer is 1 millionth of a millimeter, and it is at least 1 lakh times smaller than the diameter of a human hair. Because of its unique property, that is the small size, it has various applications and various other properties like optical, magnetic, electrical. These properties also changes when the material change from bulk to the nano size. The various applications in which the nanomaterials are used are electronics, optical, communications, and biological systems. Let us compare the size of a micrometer size, a millimeter size, and a nanometer size. We can see that from the slide, we can see the various objects like and then the head of a pin. This and all are having millimeter size. Whereas as we see that red blood cells having about the micrometer size and the various DNAs, then you can see carbon nanotubes having the nanometer size. The challenge is to fabricate and combine the nanoscale building blocks to make useful devices. Example, a photosynthetic reaction center with integral semiconductor storage. Now we have to go through the classification of nanomaterials. This, based upon their size dimension, the nanomaterials are classified into 0-dimensional, 1-dimension, 2-dimension, and 3-dimension. This classification is based on the restriction imposed by the size of nanomaterials to the flow of charge carriers. Let us see this in detail. So, 0-dimensional nanoparticles. See, we actually represent the bulk material in 3 dimensions: X dimension, Y dimension, and Z dimension. So when in all these dimensions are reduced to nanometer range, then the movement of the electron is restricted in all these 3 directions, X, Y, and Z. So the electrons cannot move in any of these direction, and the size will be like a dot. The object will be in the size of a dot. So examples for 0-dimensional nanoparticles are quantum dot nanoparticles. Then comes the 1-dimensional nanoparticles. In this, 2 dimensions are reduced to nanometer range, and 1 dimension remains large, and electrons are allowed to move along this dimension. See the diagram here. See X direction, Z direction, Y direction are there. Here, 2 of the dimensions are reduced to nanoscale, and therefore the electrons can move in only one of the direction. So that is known as 1-dimensional nanoparticles. Then comes 2-dimensional nanomaterials. In this, 1 dimension is confined to nanometer range and 2 dimensions remain large, and electrons are allowed to move along these 2 directions. Here we can see the diagram X, Y, and Z. The electrons are allowed to move in 2 of the directions. Examples for 2-dimensional nanomaterials are nanowells, nanofilms, and nanocoatings. Let us see the last classification of nanomaterials, that is 3-dimensional nanomaterial. In this, There is no confinement in nano range and electron movement is allowed in all the three directions, Z, X, Y, and Z directions. Example, bulk nanomaterials, nanopowders. So here all the three directions electrons can move. So that comes under bulk nanomaterial. So some of the other examples for zero-dimensional nanomaterials are spheres, clusters, nanoparticles. One dimension is nanofibers, wires and rods. Then two-dimension nanofilms, plates, networks. Three-dimension nanoblocks. There are various methods for synthesis of nanomaterials. Let us see one of the method, that is precipitation method for synthesis of copper oxide nanoparticles. For the synthesis of copper oxide nanoparticles, we use this, one of the method is precipitation method. And in precipitation method, two important steps are involved. One is formation of the nuclei and the second one is the growth step. So here two reagents are mixed to get an insoluble material in the solid form which precipitates out of the solution and settles down. The first step, formation of nuclei. Here the nuclei refers to group of atoms together. Initially, as the precipitation starts, few particles will approach each other forming a small mass called nuclei. So we have a precursor. And to the precursor, the precipitating agent when added, the nuclei formation will start taking place. So that is the step, formation of nuclei. In the growth step, the formed nuclei will attract one another to grow in size. So in the growth step, the above formed nuclei attract the particles present in the solution, thus increasing its size. Now this step, the second step, growth step, will decide whether the material formed is a nanomaterial or a bulk material. We should control the concentration, the stirring rate, pH, and temperature to restrict the growth of the nuclei into bulk form. So, by monitoring and restricting the growth of the nuclei, we can prepare nano-sized particles. If the growth is not controlled, this will lead to precipitation of the bulk mass, and the growth of the nuclei is controlled by maintaining suitable concentration, pH of the medium, and the temperature. So here we can see that is the general method description, precipitation method. Now in the case of copper oxide nanoparticle synthesis, the precursor taken is either a chloride salt or a sulfide salt of copper or a nitrate. Any one of these can be taken, either copper chloride, copper sulfate, or copper nitrate. And a solution form is prepared by adding non-volume of water. Then to this solution, the precipitating agent, usually an alkali, is used, like sodium hydroxide or ammonium hydroxide, is added with proper stirring. Stirring is very important here. Continuous stirring should be happening. So the moment the precipitating agent alkali is added, the small nuclei, as we have discussed, formation of nuclei will start. And with continuous stirring, the growth of this nuclei will take place. And the process, the precipitate obtained above is allowed to age. Aging is like a curing process, so that it will grow into the size of nanomaterial. So by controlling, as we have discussed, by controlling the temperature, pH, solution, concentration, we can control the growth of the nuclei to the nano size. Then the solution, after allowing it to age, the solution has to be washed for several times till it is free from the counter ions, so that the other ions should not interfere in the nanomaterial preparation. So thus the obtained precipitate has to be dried. and then subjected to calcination at a desired temperature to obtain the copper oxide nanoparticles. So we can see the reactions here, what is happening when the precipitating agent is added to the precursor, that is the copper chloride plus sodium hydroxide. By controlling the temperature, pH, stirring rate, and the capping agents, we get copper hydroxide plus sodium chloride. This one formed, the product formed has to be subjected to calcination, that is high temperature heating, to get the product, the nanomaterial copper oxide. So this is the preparation of copper oxide nanomaterials from the precursor copper chloride or copper sulfate. So these are the, so after getting the copper oxide nanomaterial, we have to send it for characterization study, which will determine the size of the synthesized material. So this, like this, we can see some examples of nanomaterials. See, gold nanoparticles, Buckminster fullerenes, iron platinum nanospheres, see titanium nanoflower, silver cubes, tin nanoflower, like that. So this is the precipitation method for the synthesis of copper oxide nanoparticles.